Good morning, everyone. So today I'm gonna start off with something that I finished last time. However, I'm gonna go over one point there, which I think I forgot to mention or emphasize, which is this. In the Chebyshev's rule, remember, this percentage of data is included if you move, let's say, k standard deviations to the right, k times s, or k standard deviation to the left, x bar minus ks. Normally, we write it as x bar plus or minus k times s. S is the standard deviation. Now, where k is the number of standard deviations that you move in either direction. The thing that I think I forgot to mention last time, even though it's here, this k must be greater than 1. So this Chebyshev's rule works only if your k is greater than 1. If it is less than or equal to 1, it does not apply. Okay? And remember, it includes at least this percentage of data. Okay? At least this percentage of data within the standard deviation. So if you move 2 standard deviations, it is going to be 1 minus 2 square, right? Which is, if you simplify it, is going to be 1 minus 1 quarter or 1 over 4, which is 3/4, right? Which is the same as 0.75 or 75% of the data, at least. At least 75% of the data is included if you move 2 standard deviations to the right. So that means, let's say this is your some data distribution and that's your x bar. And if you go 1 standard deviation, 2 standard deviations, so x bar plus 2 standard deviations, go 1 to the left, 2 to the left, x bar minus 2 standard deviations, then in between this point and this point, you'll include at least, remember, at least 75% of the total data points. Okay, it is an at least, once again, at least. So what is outside? Remember, here and here, at most. Complement of at least is at most. So here it will be at most. So this is what it is. Is it okay, everyone? Chebyshev's rule. So remember, the k must be greater than 1. All right. Now let's go ahead and continue with the new topic. And also, just a quick announcement. This coming Monday is a holiday, so there will be no class. Okay, it's President's Day weekend. So Monday, no class. So next time I will be seeing you guys is on Wednesday. So after today's class, I'm going to give you a new set of homework to work on. All right. Do the best you can, because by the end of today's lecture, I don't think I will be able to cover everything that I wanted to cover. Okay. So make sure that you do the ones that you can. All right. And if you cannot do anything, just wait, and I will be covering those topics on Wednesday's class, right? Now, the new topic, probability. You kind of have, all of you have intuitive sense of what probability is. You kind of describe it in a sense like, what are the chances of something happening? You have the intuition what probability is. What are the chances? What are the likelihood of something happening? As an ordinary person, that's what you think, right? So that's exactly what probability is. Probability is associated with an event, okay? Probability in and of itself, by itself, it's an abstract concept, but you have to apply it to a specific event. So if you toss a coin, what are the chances that you will get a head? Okay, if you roll a die, what are the chances that you will get the number 6? So these questions back to the definition of probability. Officially, how we define probability is this. This may sound a little bit dry. The probability of an event is the proportion of times it happens compared to the total number of times, total number of tries, total number of times one tries. Okay, that's what it is. So think of a very simple scenario. You have a coin, let's say you toss it 100 times, and you observe how many times head showed up. So let's say 52 times head showed up out of 100 times. So your probability, you kind of would think that is 52 out of 100, or approximately 0.52. But 100 is a very limited number, small number. It's technically, the way we define probability is this. If you toss a coin many times, a large number of times, in theory, if you toss it infinitely many times, you will see the ratio of heads divided by the total number of tries, it would approach this number, 0.5 or 50%. Okay, with 100 trials, it might even be the case you get 55 heads out of 100 tries. So you'll be having 55 over 100, which is 0.55. That doesn't mean that the probability of getting a head when you toss a fair coin will be 55%. It actually is a limiting value. What do I mean by limiting value? That means if you try, think of it this way. Let's say you got 55 out of 100. Let's say you try increase it by multiple of 10. You tried 1,000. Let's say you got 503 out of 1,000. What if you tried 10,000 times? Okay, 5,005, you got 10,000 times trying. Now you can keep trying this, and you will see these ratios. Look at this ratio. This is 0.55. This is 0.503. This is 0.5005. And you can keep trying, and you will see this sequence of numbers. You can try it infinitely many times, approaches 0.5 or 50%, which is to say that the probability of getting a head when you toss a coin is 50%, or equivalently, probability of getting a tail when you toss a fair coin is 50%. I use the word expression fair coin. What it means is it's an unbiased coin, regular coin, okay? It's unbiased. You don't load it in one way or the other, or you don't do anything to the coin so that you get a specific or a desired outcome, okay? So that's what I mean by fair coin. It's unbiased. It's a natural coin as it is. So let's go back here. So proportion of times the desired event happens divided by the total number of times you tried. Okay, and this is exactly what we defined right here. See, look at this. Probability of some event A, probability of some event A is the same as the number of times that event A has showed up or happened, divided by the total number of trials, or total number of times you have tried. This is also known as relative frequency definition of probability. This is also known as relative frequency definition of probability. That's what it is. So n is the total number of times you tried, n with a subscript of a that denotes the number of times the specific event A has happened, divided by the total number of tries. Maybe I should make it a little bit clearer. So probability of some event A is the same as n sub capital A, that the number of times the event A has happened, divided by the total number of trials, and it is called frequency definition. Frequency definition of probability. And that's probably what you want to keep in mind. Very simple. And there are other ways of defining probability, which I briefly will touch on, but essentially this would do the job for us, okay? Essentially, this would do the job, is the frequency definition. Now, when you're studying probability, you kind of have to learn some terms. Trials or experiment, you kind of already know what it is. Trials or experiments. It's a controlled process in which the outcome is unknown. Okay, we talked about trials or experiments in the case of COVID-19 vaccine. You can think of it this way. If a patient or if a person takes the COVID-19 vaccine or coronavirus vaccine, that's a controlled process, okay? So you could think of it as a trial or experiment. In the medical industry, they call it trial, okay? More so trial than experiments. So you can interchange these words, trial/experiment. Now, in the process, when a person takes the vaccine, he or she doesn't know whether it's going to be effective or not. So that's an outcome which is uncertain or unknown. Uncertain or unknown, okay? So a trial or experiment is a controlled process where the outcome is unknown. More obvious or straightforward example for you is gonna be toss a fair coin. Toss a fair coin, okay? In that case, before you toss the fair coin, do you know what the outcome is going to be? For sure, the answer is no, we do not know. We don't know, right? You don't know what the outcome is going to be for that particular trial. So the process of tossing a coin is the trial or experiment, okay? An event is the outcome, okay? An event is the outcome of an experiment or trial. So when you are tossing a fair coin, it's a trial or experiment. Getting ahead is the outcome. So that's going to be your outcome. Getting ahead is going to be your outcome. So these are terms you kind of have to get familiar with. You already have seen it once before in the context of vaccination, or in the context of what was the topic that we were talking about? I forgot. But you have seen it before. Oh, designing experiments. Okay. Over there, you have seen similar terms: so trial, experiments, and events. Remember, event is a certain outcome. Now, if you roll a die, for instance, if you roll a die and you're looking for an outcome which is, let's say, 6. You're looking for the outcome 6. So rolling a die would be an experiment or trial, and your particular event you're looking for is 6, that 6 shows up. It could be any of the other numbers, 1, 2, 3, 4, or 5. It really doesn't matter. So far, what we have defined are 3 things. Probability. Probability, in layman's term, it is the chance or likelihood of something happening. What is the probability that you will finish the semester with an A? Okay, there is a chance that you will finish the semester with an A in this class, in statistics, let's say. So that's an event, you getting an A, and the probability is associated with the event, right? That probability that you will get an A. And also you can think of what is the probability that you will finish college this year and land a good job. So you can think of like ordinary person, how an ordinary person will think. Like, probability is something for which the outcome is uncertain, and there is a chance or likelihood, or there is a percentage we can assign to it, right? This percent chance that this is going to happen. You guys know about percentages, right? There is a 60% chance that you will get an A in this class, or there's a 70% chance that you will get an A in this class. Now, the simplest way we define probability is that number of times your desired outcome has happened divided by the total number of times you tried. Okay, so in essence, is the event divided by the trial / experiment. So number of times the event has happened, which is n sub a, divided by the number of trials or experiment, which is n. So that's the frequency or relative frequency definition of probability. Now that this is clear, let's go ahead and talk about some other definitions. Simple events and sample space. These are two important things you may want to keep in mind. Simple events. What is a simple event? Simple event is an event. An event is a simple event if it can happen in only one way. Can happen in only one way. It cannot happen in multiple ways. So think of this as an example. Like if you toss a coin and let's say, what is the probability that you will get a tail, which is 50%, but the event tail itself, it can happen in only one way. It cannot happen in multiple ways, okay? So a simple event is an event that can happen in only one way. It is exactly one outcome. When tossing a fair coin, getting a head one way, or if rolling a die, one can get the number 6 only one way, right? So if you roll a die, you can get the number 6 only in one way. However, think of this scenario where things may not be simple. Let's say you roll 2 dice, okay? Roll 2 dice. Dice is plural, I think, right? Die is singular, right? You roll 2 dice, and then you are looking for the outcome, let's say 8. So your event A is going to be the outcome 8. Now you can get 8 in multiple ways here. This, even though it's a simple event, even though it's an event, it can happen in more than one way. Therefore, it is not a simple event. 8 could be 6 plus 2, right? You have two dice. One could be 6, another could be 2, 8, or it could be 4 plus 4, 1, 4, the other one is 4, or one could be 5, the other could be 3. Do you see? The same outcome, but it could happen in 3 different ways or more than one way. Therefore, we would describe this event as not simple. Not simple. Whereas if you roll a single die, one die, okay, the outcome could be one of these numbers, 1, 2, 3, 4, 5, and 6. It will be one of these numbers, but each of these numbers or each of these events, you can think of these numbers as individual events. Each of these events can happen in only one way. Okay, so therefore this must be simple events. So when you roll a die, outcome could be one of these numbers. Let's say you are looking for outcome 4. That's a simple event. Simple event. All right. Now, so in an experiment or in a trial, collection of all simple events, is called, remember, sample sample space. In an experiment or trial, the collection of all the simple events is called sample space. So this is a definition you should know. What is a sample space? What is a sample space? And what is a simple event? Easy way to remember is example 1. Toss a coin. Easy way to remember. Toss a coin or fair coin, okay? Getting a head is a simple event because this can happen in only one way. Getting a tail is a simple event because it can happen in only one way. In this trial or experiment, these are the only two things that can happen. So your sample space is gonna be head and tail together. Remember this example, that would really help you understand it. Once again, toss a coin. Getting a head is a simple event because it cannot happen in multiple ways. Or getting a tail is a simple event because getting of tail cannot happen in more than one way. Together, they create the sample space because these are the only things that could happen when you toss a coin. Now, don't tell me that, oh, if I toss a coin, what if it lands on the side? I guess in theory it could, but in reality it has never happened. So if you toss a coin and let it land on a flat surface, flat and hard surface, I think it will never, you can try it infinitely many times almost. It will never land on the side, but even though in theory it could. Okay. It just reminds me of a very interesting example from physics. Many years ago, I used to study physics. So this is a funny example. Like, let me finish the example, then I'll tell you the. It's not a story. It is a story / it is a fact as well. So this is one example. Sample space. Another example you can think of is roll a die. If you roll a die, getting the number 1 is a simple event. Getting the number 2 is a simple event. Getting the number 3 is a simple event. 4, 5, and 6. Each of these events are simple events because they cannot happen in multiple ways. Unlike this guy, if you roll 2 dice, you're looking for the outcome of 8, it could happen in 3 different ways, which is more than 1. So long it happens, or it could potentially happen in more than one way, then it will be not a simple event. Or I don't know if we use the word complex event. That's not so common. We say either simple event or not a simple event. However, these guys are simple events each individually. And when you roll a die, there is nothing else that could happen, right? When you roll a die, you will get nothing but 1, 2, 3, 4, 5, or 6. And together, they form a sample space. In a trial or experiment, the collection of all the simple events make the sample space. In a trial or experiment, the collection of all the simple events make it sample space, or makes the sample space. If you remember these two examples, I think you will get a good sense of what is a simple event and what is a sample space. Now you can take these ideas and apply it to other specific examples that you might be interested in, okay? Try to understand it with very simple, try to learn it with very simple examples, like tossing a coin, rolling a die. So, having said that, is everybody okay with all these definitions? We discussed about few things. We discussed about the definition of probability, which is the relative frequency definition. We talked about trials or experiments. We talked about events, okay? Then we talked about simple events. We talked about sample space. So there are 5 different things we talked about. And this is a definition, and you need to kind of learn these definitions in order to be able to understand other concepts related to probability. Anybody has any question before I move on to the next topic? Anyone? Everybody okay? All right, looks like no question. Erika Robles, any question?
No, I'm good.
Okay. All right. Ulysses, any question about the definitions so far?
I'm good.
You're good? Okay. Now let me give you the story that I wanted to tell you about, tossing a coin and how it relates to another example. If you toss a coin, in theory, it could land on the side, probably in theory, but in reality, it will never happen. Another similar example is this. Let's say you're in a room, okay? Think of room as a 3-dimensional thing, right? So you're inside a room, and there you are. Okay? That's my artistic skills. You can see how great of an artist am I. So you're inside of a room, and air molecules, you have to breathe to survive. Air molecules, they are randomly bumping into each other. Think of, you can't see it, but think of these as little balls, okay? Little balls. They're always bumping into each other randomly and moving around. Air molecules are not fixed. So they're always bumping into each other, but they're such small particles that you cannot see them. Now, in theory, it is possible that all these air molecules bumping into each other in such a way so that all the molecules end up in this corner. Okay? In theory, it is possible that all the molecules end up in this corner. Then you have no air and you will die. It is true. I'm not making it up. If you hypothetically think of a room where you have no connection to other outside world, and you are inside of the room, inside of this room, and you have enough oxygen and air supply there so that you can survive. Now, in theory, all these air molecules could bump into each other in a random way, and all of them gather right in this corner, leaving you with no air, hence causing you to die. It is, in theory, possible. In practice, is it possible? No. It probably will not happen. But in theory, yes. So that's kind of like if you toss a coin, okay? If you toss a coin, you either get a head or tail, but in theory, you could land on the side. Neither of these true, but it probably won't happen. All right, let's do this example. A couple wants to have 3 babies over the next 3 years. Create a sample space for the possible outcomes. Couple wants to have 3 babies over the next 3 years, and you need to create a sample space for these possibilities. Now, here is one of the things I'm kind of assuming that is going to be either boy or girl, no other gender. and no twins of the same gender or anything, okay? Or no twins at all. Keeping the example simple. It's going to be either boy or a girl, and they will have one child or one baby per year. Now, assuming that order does matter, we'll talk about it later. Assuming that order does matter, okay, create a sample space. That means what are all the possible simple events? So I should probably add this order matters, okay? Order matters. That will make it a simple event. Order matters. Now, go ahead and think about it. I'm going to give you just about a minute to think about this, okay? Just take a minute and take a pen and paper and try to write down the simple events. Just a minute I'll give you. Okay, guys. So go ahead and tell me, somebody, what is it you have done, and give me an idea.
So would for the first question, find the probability of having two boys and a girl, would it be BBG?
Yes, but even before answering the questions, I kind of wanted you to create the sample space first for this scenario. So if the couple wants to have 3 babies over the next 3 years, what is the sample space? So that's what I was trying to have you do. So any other suggestion from anybody?
So what are you like, what do you mean by the question? Because for the sample space, that is when you like list the probability, right?
List the outcomes, not the probabilities, list the outcomes, or
So,
list the simple events. Yes.
okay. So for this instance, just because having a child, it's a 50-50, you don't know what you're having.
Correct. Correct.
So would there be like many different ways to list the beginning?
Yes, you're correct, Alicia. There will be many different ways of listing it. Yeah, that's the right start. And any other things? Anybody? All right, let's go ahead. Thank you, Alicia. Let's go ahead and do it this way. Year 1, year 2, year 3. Okay. Year 1, year 2, and year 3. So I'm gonna just do it in a very simple way. For first year, they could have a girl. Second year, they could have a girl. Third year, they could have a girl. Okay. Then they could have a girl, first and second, and the third year boy. They could have a girl in the first year, second year a boy, a third year a girl. They could have a girl in the first year, boy in the second year, boy in the third year. Or they could have boy in the first, second, and third, boy, boy, girl, boy, girl, boy, or boy, girl, girl. That's all the possibilities. Now you might be thinking that I'm doing it so naturally and quickly. I'm not a genius. When I designed this problem many years ago, I had to think about, what are the different possibilities, and it didn't come to me naturally. But over the years, I developed a strategy, and that covers everything. First of all, the rule is there are 3 different years, right? Year 1, year 2, and year 3. For each of these years, there are 2 possible outcomes or 2 possible events, right? So it will be total of 2 cube. So this could happen in 2 ways, this could happen in 2 ways, this could happen in 2 ways. Together, they could happen 2 to the power 3 or 8 different ways. If you count them, you'll be seeing that there is there are 8 different simple events. Remember, order matters here, okay? So that makes these events simple events. They cannot happen in more than one way. Is this clear to everybody? So this is your sample space, okay? This is your sample space. Each of these is a simple event. Each of these is a simple event. Now here, I kind of want to bring this to your attention, even though I didn't mention it in the problem, which I probably would add, but I clarify it to the students. If order doesn't matter, then events may not be simple, because if you're talking about having 2 girls and a boy, girl, girl, boy, okay, 2 girls and a boy, there is one and there is another one, 2 girls and a boy. So it could happen in multiple ways. But if order matters, then in that case, girl, girl, boy, that's an event, okay, by itself. Boy, girl, girl, that's another simple event by itself. So these individual events become simple events, okay? And the collection of all the simple events is sample space. So when I asked you to create a sample space, okay? My expectation was that you'd be listing something like this, okay, or at least get started like this. So when I asked about creating the sample space, I was expecting this list. Now, what if instead of 3 years, if we had 4 years, okay, year 4 as well? In that case, the number of simple events, okay, if I were to ask you for 4 years, the number of simple events is going to be 2 raised to the power 4, which is 16. So instead of 8, you're going to get 16. What if I asked for 5 years? So then it's going to be 2 to the power 5, or 32 different ways. But I'm probably not going to ask you anything crazy, because I'm not even ever going to ask you to list it, probably. All right. But this is a simple enough, yet I can list it in a way so that it doesn't consume too much time and do the problem. The main concept is to give you the idea of probability and how it works. Now, this is how you'd create the sample space, okay? Collection of all simple events. Now, based on this, I want you to answer these questions. Alicia, you were kind of jumping ahead and trying to answer these questions. Now, find the probability of having 2 boys and a girl. So we are looking for the probability of 2 boys and 1 girl, right? 2 boys, let's just do this. Probability of 2 boys and a girl, or 1 girl. So now let's look at this and use a different color. 2 boys and a girl. Where do you see? There is a 2 boy and a girl. Is there any other 2 boys and a girl? There is a 2 boy and a girl. Is there any other 2 boys and a girl?
Yeah.
Where is it?
Where it says boy and then girl, boy. At the bottom of the...
Oh, okay, right. 2 boys and a girl, right? So that would be 3 different ways, right? Out of how many different ways? 8. So it's 3 out of 8. Now, this kind of leads to another definition of probability, which is this. So that's also a probability. So I'm going to write number of ways an event can happen divided by the total number of simple events. Look at this particular event. What is the event? My event, let's call it A, probability of A is the event that the couple gives birth to 2 boys, okay, and 1 girl. That's the event. My event is that the couple gives birth to 2 boys and 1 girl. So that is gonna be the event, probability of event A. So the number of ways event A can happen, I should say number of ways event A can happen divided by the total number of simple events. Number of simple events. That's exactly what we did here. Number of ways the couple can have 2 boys and a girl, or number of ways event A can happen is 3 different ways, right? We just found it. This one, and this one. And what is the total number of simple events? Sum of all of these, which is how many? 8. So that's why we have 3 out of 8. I just gave you a second definition of probability, which is probability of some event A is equal to number of ways event A can happen divided by total number of simple events. The screen is a bit cluttered. Are you guys being able to follow it, or I'm making it a bit clumsy for you, or a bit cluttered for you rather? Are you able to see it? Everybody, is it okay?
Yeah.
It's
Yes.
fine? Okay. Because of all right, so I'm gonna go ahead and I hate to clean it up because I have to go back and do the rest of the problems. So let me just give you another example. Now, this is the second definition of probability. Remember, the last definition was probability of an event A was the frequency, relative frequency, number of times event A has happened divided by the total number of simple events, right? That's the relative frequency definition of probability. Right? That's the relative frequency definition of probability. This is the simple events definition of probability. You can think of it. I don't know what's the exact definition name they use, but it really doesn't matter what they call. So long we understand the concept, it's just another way of defining probability. Now look, if you toss a coin, so I'm going to apply this definition for coin and rolling a die. Your event A is that you get a head. How many ways can event A happen? When you toss a coin, a fair coin, how many ways you can get a head? Just one way, isn't it? Just one way. If you toss a coin, what is your sample space? You either get a head or what? A tail. How many simple events are there? 2. So your probability of getting a head or probability of event A is going to be number of ways. So let me use a different color. Number of ways the event A can happen, which is 1, right? Divided by the total number of simple events. In our case, the total number of simple events is 2. So do you see the probability of getting a head is half or 50%. That's another way of deriving probability associated with an event. In exactly the same way, if my event is B, which is getting a tail, right? How many different ways event B can happen? Just only one way. How many total simple events, which is 2. So probability of event B is going to be 1/2 as well. Now let me go ahead and give you another example, which is roll a die. let's say your event A is getting the number 6. So your probability of event A is gonna be number of ways this event A can happen. But event A is a simple event, right? Like getting ahead is a simple event because it can happen in only one way. So event A can happen in only one way, divided by the total number of simple events, divided by the total number of simple events. So this one represents the number of ways this particular event A can happen, divided by the total number of simple events. Now, when you roll a die, how many simple events do we have? Can somebody help me out? If you roll a die, how many simple events do you have?
6.
6, exactly. Why 6? Because you can get 1, 2, 3, 4, 5, or 6. So it should be 1 out of 6. That's exactly what it is. When you roll a die, what is the probability that you get a 6? It's 1 out of 6. Now, if I define event B as getting 3, what is the probability of event B? Can somebody help me out? Number of ways you can get event B, which is 3, right? How many ways can you get a 3 when you roll a die? Only one way, right? Divided by the total number of simple events, which is 6. You can see how we can go back and forth between these two definitions. I hope that it makes a little bit sense. Hopefully, it'll get better and better. And my recommendation is that the class notes that I send you, please read them. Oh, by the way, I just sent you the class notes, so you may want to check your email. Okay, for this lecture, I just sent you the class notes. So please look at these lecture notes. You know, multiple times, read it multiple times and watch the video, then it will start to come together. Initially, everything looks cloudy, but then it becomes clearer as you read it more and more number of times. Okay, now I don't have a choice but erase this because it's, so year 1, year 2, year 3, boy, 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 girl, boy, girl, boy, boy, girl, 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 boy, girl, boy, girl, and girl, girl, oops, girl, boy, and boy. So that's what it is gonna be. So find the probability of 2 boys and a girl. We did it. Now find the probability of having all 3 girls. How many ways can you have all 3 girls? There is only one way. Out of how many? 8. So there you go. Find the probability of having at least 2 boys. So probability of at least, so this is an interesting one, at least 2 boys. Now remember, at least 2 boys means what? It could be 2 boys or more. 2 boys or more. So this in essence is the probability of 2 boys plus the probability of 3 boys. That's what you're finding. You cannot have 4 boys because the couple is having only 3 babies over the next 3 years. So the probability of 2 boys and probability of 3 boys. Okay, probability of 2 boys and probability of 3 boys. So what is the probability of 2 boys? Okay, so if you look at it, let me just go ahead. 2 boys I see here. I see here 2 boys. I see here 2 boys. So that's gonna be, the first one is gonna be 3 out of 8 plus The second one is going to be probability of 3 boys, which is this one, 1 out of 8, which is going to be 4 out of 8 or 1/2, because 4 goes into 8 2 times. So probability of at least 2 boys is 1/2 or 50%. 1/2 or 50%. That's what it is. Next one is probability of having no boys. That means what? Probability of all girls. That means probability of 3 girls. How many ways can you have 3 girls? There is just only one way. It's 1 out of 8. Probability of having more than one girl. More than one girl. So probability of more than one girl, which is this. This is going to be probability of 2 girls plus the probability of 3 girls, right? Like probability of 2 boys and probability of 3 boys. This is exactly like this. It's going to be probability of 2 girls, you can check it, is going to be 3 out of 8. Probability of 3 girls is 1 out of 8, which is 4 out of 8, which is 1/2, because 4 goes into 8 twice, which is 50%. Now, probability of having more than 3 boys. So probability of more than 3 boys. What is this one? Can anybody help me out? What is the probability of having more than 3 boys? Anybody?
It's going to be 0.
Who is talking?
Jerry.
Jerry? Jerry? Is that right?
It's Jerry.
Jerry, okay. Yes, it is 0. Why?
Because the couple can't have, well, they don't want more than 3.
Yeah, exactly. They are having only 3 children, right? So they cannot have 4 boys. The most they can have is 3. Now, I'm going to give you guys a little semi-break right now, but I kind of want you to do this during the break. So we'll take a 15 minutes break, so we'll meet at 9:45. I want you to try the next problem during the break a little bit. A simple quiz consists of true and false and multiple choice questions with 6 choices. Create a simple sample space. So I'm going to give you this hint. Question 1 is true or false. And question 2 is a multiple choice with 6 choices. So 1, 2, 3, 4, 5, and 6. And that's all you've got. You have a simple, very simple quiz, 2 questions. Question 1 is a true or false. That means it has 2 choices, right? 1 or 2. I use labels true or false. And question 2, however, has 6 choices, 6 possibilities, 1, 2, 3, 4, 5, and 6. Now you're trying to take this simple quiz. So let me ask you this. When you take this simple quiz, what is the sample space? That means I'm asking for what are the possible simple events. So I'm asking what are the possible simple events. So having said that, next 12 minutes or so, go ahead and try it, and I'll be asking you questions once we get back at 9:45 exactly. Okay, folks, let's go ahead and get going with this problem. So what do you think? What did you do? Anybody wants to help me out?
You make two columns, and one of them is for true and false, and then the other one has the question 2 answers. And the way that I did it was on one column I did true and false, and then the next one 1 and 1, true and false, 2 2, true and false, 3 3. So you
Yeah, go ahead.
so that's how I did it. It should have 12 different outcomes.
Oops, sorry. I should start a new company. Zoom is not enough to teach. It's an excellent tool, but it is not enough to teach. We need a tool where you can write and I can see, and I can write and you can see. We can sort of like directly write on the screen, where it's more interactive. You can do something like this with Zoom, but then I have to give you control of the screen and this and that. Oh. No, I think even without giving control, you can write on the screen. Can anybody write on the screen with hand? Nobody? Okay. I know that you can write, but we need more interactive tool for learning math, where we'll have symbols and things like that. We can easily drag and drop. All right, Jerry, I didn't quite understand 100% what you said, but I think you did it right. The reason I'm saying that you did it right, because your explanation fell along the line of what I was thinking. And so clarify me if this is exactly what you did. So there are two options for the first one. If you answered true for the first one, for the second one, you could answer 1. Or if you answered true for the first one, second one, you could answer 2. If you answered true for the first one, second one, you could answer 3, or 4, or 5, or what? 6, correct? If you answered false for the first one, second one, you could answer 1, or false for the first one, second one, 2, false, 3, false, 4, false, 5, and false, and what? 6. Is it what, Jerry, you were thinking?
Yeah.
Okay, perfect. I hope some other folks have thought the same way. So that's your sample space. Each of these events are simple events. Each of these events are simple events. And what is your sample space? Collection of all the simple events. So that is your sample space. Now, based on this, you can answer questions. Now, let's go ahead and answer the questions. Now, one thing I kind of want to highlight here is this. Let's say one of these choices has to be correct, right? You don't have a choice. You're taking the quiz and you'll be answering both the questions. So one of them has to be correct response for both of them. It doesn't matter which one you pick. Let's say I pick T6, okay? True is the correct response for the first question, and number 6 is the correct response for the second question. So T6, you could pick F1, it doesn't matter. So let's say T6 is the correct response. You could, by the way, you could pick any of the 12 possibilities as correct response. Then the others will be not 100% correct. So find the probability of getting both questions right, which is this one, right? T6. So probability of both questions right is going to be probability of both correct is going to be 1 that can happen in only one way out of how many different ways? How many different simple events? 12. So your chances of getting it right by random guessing is 1 out of 12. Next question, the probability of getting one question right. One question right. The probability of getting one question right. What is that probability? Now, can anybody help me out with this? I want you to do it yourself as well, because otherwise you will not be learning. Even though we have limited time in the class, but in the homework you'll be doing it, but even in the class, I want you to be proactive and try it. Please try. What is it? So the probability of one question right, I should say exactly one question, probably. Okay. Exactly one question. The probability of exactly one question right. So let's look at the first row. If you selected first row, would you get one question right? How many times would you get one question right? One question right. See, this is gonna, if you responded to T1, you'll have one right, T2, T3, T4, and T5. There are 5 different ways you will get exactly one question right. If you look at the second row, everything is false for the first question, okay? Everything is incorrect response, because first question, the correct response is T, second question, the correct response is 6. So if you look at the second question, second row, for all of them, the first question is wrong, but there is only one, this one, for which the second one is correct. So there is one way you can get it right here. So 1 here, 5 on the top, right here. 1, 2, 3, 4, and 5. 1 plus 5 is 6. So 6 out of 12, which is 1/2 or 50%. So there is a 50% chance that you'll get exactly one question right. Find the probability of getting no questions right. That means both wrong. Probability of both wrong. Find the probability of both wrong. Now again, you have to look at this sample space. When would you get both wrong? If you look at the first row, nothing you can get from there both wrong, because each of these choices in the first row has at least one correct, at least one right. That means first question has a correct response of T, right? True. So everything in the first row, everything in this first row has T. So everything in the first row has at least one correct, but this one has 2 correct. But if you look at the second row, these 5 has both wrong. Do you see that? This 5 has both wrong. We want both wrong. However, this one has 1 correct. So that one we have to exclude. So number of ways you can get both wrong is 5 out of the total number of possible ways, or total number of simple events, which is 12. So your probability is 5 out of 12. And the last one, find the probability of getting at least one question right. Probability of at least one question right. Which is probability of at least one means probability of one question right plus probability of 2 questions right. Can you have 3 questions right? The answer is no, because there are only 2 questions. You could write it indefinitely, probability of 3 questions, 4 questions, 5 questions, but all of them are going to be zeros. So don't worry about that. Probability of one question right, okay, we got it already, which is this one, probability of exactly one question right, which is 1/2, plus the probability of getting 2 questions right, we also got that one, which is 1/12. If you do the math, it's gonna be 6/12, which is 1/2, right? Plus 1/12, so it's gonna be 6 plus 1/12, which is 7/12. So the probability of getting at least one question right is 7/12. Now the next one is this. Find the probability of getting at most 2 questions right. So the probability of at most 2 questions right. What is the probability of getting at most 2 questions right? Anybody has that? Anyone? At most 2 questions right? Anybody wants to? Araceli, would you want to try?
I'm trying to figure it out right now.
Okay, good. Anybody else? Juan, Perez? Juan Perez, would you want to try? Tenok Ortiz? Anybody?
I would answer it, but I'm still kind of new to this, so I don't really fully understand it.
Okay.
Like when I did the homework, I was able to do the first half, but once I got to the other half, like where it started with all the numbers, I really didn't. I got lost. Like I didn't know.
Okay. Did you watch the video?
The class notes that was sent to us.
I sent the class notes, but that's different. I actually sent the videos of the lectures as well. So this lecture is being recorded and I'm sending it to you. So you may want to watch the video because all the homework problems, the topics that you need to know, I go over those in the video, in the class, in the actual class. So if you get stuck with something, go ahead and watch the video, read the class notes if it helps. And then even after that, if it is not clear, by all means, please bring it to the class, okay? Maybe other students will learn from it too, because they may have similar questions. So anybody, if you get stuck with the problem, homework problem that I covered the topic in the class, but you're not sure, still getting it wrong, bring it to the class. I'll answer those, all right?
Thank you.
All right, probability of at most 2 right means what? At most 2. I kind of like to give this example. This is a sales gimmick. Somebody says 70% off, then in fine print up to. What they're saying is at most. You see sales ad, it says 70% off. People are thinking, oh, 70% off, let's go. But in fine print, it says right in the bottom up to, which is to say at most. It could be 70% or less. And if you go to the store, you'll see at 70% discount, they have something that you probably don't want. The things that you want are probably not at 70%. It's much less discount or no discount. The technique or trick they use here is to kind of take advantage of your you know, what is the right word I'm looking for? Basically take advantage of you, let's put it that way. So up to or at most, up to or at most. So it's exactly like this. Probability of at most 2 questions right, meaning that probability of getting no question right, that means 0 question right, plus probability of getting 1 question right, plus probability of getting 2 questions right. Correct? So that's like at most. Up to 70%, it could be 70%, 60%, or 50%, 30%, 40%, 25%, 0%. That's also up to 70%, right? That's exactly what this problem is. At most 2 questions right. You can have 2 questions right, 1 question right, 0 question right, which is what? No questions right. If you're taking a quiz of 2 questions, that's all that could happen. Nothing else could happen. These are all the possible events that could happen. Think of it this way. If you're taking a quiz, all the possible events are this. All the possible outcomes are this. Either you get 2 questions correct, or you get 1 question correct, or you get no question correct. Getting 2 questions correct equivalently 0 wrong. Getting 1 question correct is 0 wrong. Oops, W, not R. 0, 1 wrong. Getting no question right means 2 wrong. It's equivalent, which is, by the way, 100% or 1. You can do it by looking at the simple events. No question correct, we found it 5 out of 12. So I'm going to do it here. No question right, 5 out of 12, plus 1 question right, which is 6 out of 12, plus 2 questions right, which is 1 out of 12. If you add it, 5 plus 6 is 11, plus 1 is 12 out of 12, which is 1, which is 100%. The same question could be asked slightly differently. Probability of at most 2 questions wrong. Probability of at most 2 questions wrong. You can go ahead and do it. Which is also, by the way, going to be 100% or 1. This is a complete example of where you get the concept of simple events and sample space, and how to use simple events and sample space to find the probabilities. These 2 examples kind of in details give you the ideas and definitions associated with probability. What is an event? What is a simple event? What is an experiment or trial? How do you find probability using sample space and simple events or events? And these 2 examples cover everything. And if you understood this, you understood a good portion of probability that I would be covering. The rest is going to be a bit more harder, but those are more formula. But this is just basic. Your foundation is being built right here. Before I move on, any question from anybody? No question. Okay, rare or unusual events. Rare or unusual events are events that are extremely unlikely to happen. Rare or unusual events are events that are extremely unlikely to happen. For instance, Mega Millions. This is my favorite examples to give. Mega Millions. This is a lottery, right? And very recently it went up to $1 billion US. That's kind of crazy. And somebody actually won it. A woman from Michigan, she won it. So Mega Millions is played twice a week, I think. Now, in theory, it is possible for one person to win the Mega Millions 2 times in a week. It's possible. You play it on a Saturday and a Wednesday, whatever days they have the drawing, and you win it in one single week, you win the Mega Millions twice. It is possible. But how likely is it this event to take place? How likely is it that this event will happen or the person will win the Mega Millions twice in a week? Extremely unlikely. It is possible. It is possible, but it's not probable. It's not going to happen probably. But in theory, it could happen. And why did I give you this example? Just to make sense to you that rare events or unusual events, events that are very unlikely to happen. By the way, I gave you an extreme example. When we say rare events, it's not as extreme, okay? Sometimes people define, so it's subjective. Don't think it's very precise. Sometimes people say an event is unlikely or unusual if the chances of it's happening less than 5%. Okay, less than 5%. If the chances of it happening is less than 5%, that's what it is. Rare events are events that are unlikely to happen or less likely to happen, not unlikely, less likely to happen. All right, properties of probability. Now let's go ahead and talk about the properties of probability. We have defined probability, but we have not talked about the different attributes or characteristics of probability, okay? What are the different features of probability? So let's go ahead and do that. First of all, please don't do this. Probability can never be greater than 1 or less than 0. So probability is always going to be between 0 and 1. Or equivalently, probability will be between 0% and what? 100%. And on the number line, you can think of it this way. This is 0 and this is 1, right? It could be between these 2 points. Let's highlight this, including the boundary points. It could be 0 as well as it could be 1. So I'm highlighting everything in between. So that's your range. So if I ask you and you give me this, right? Let's say I asked you, and what is the probability of some event? You said 1.2. That would make me very unhappy. That tells me that you missed the boat. You didn't follow the basics. So probability of an event A must fall between what? 0 and 1. That's exactly what it says. 0 is less than or equal to some probability of, probability of some event A, and it is less than or equal to 1, which is equivalent to saying that it falls in this interval, or it falls in this interval, 0% and 100%. Number 2, probability of the sample space S is 1. So that's another interesting thing. Probability of S is always 1. Very simple example. Toss a coin. What's your sample space? Either head or tail, right? That's your sample space, let's say S. Your sample space S, head or tail. Now look, if if you toss a fair coin, you can get head or you can get tail. Nothing else would happen. So the probability of the event, so sample space, this is the event. Probability of S must be probability of head plus probability of tail, which is 1/2 plus 1/2, which is 1. So remember this. In general, probability of the sample space is always 1, because that's all the things that could happen, right? So in the most recent examples I had, it was T1 through what? T6, right? And then F1 through what? F6. That's your sample space. If you take the quiz, okay, that's your S. What is the probability of S in this context? It has to be 1, because if you take the quiz, or 100% is the same thing, by the way. 1 is the same as 100%. If you take the quiz, you must have to land in the sample space. You must have to be answering one of these 12 possibilities. So your probability of the sample space is always 1. So that's the second attribute. So first and the second, let me use a different color so that you can see it clearly. First one we talked, second one we talked. This is a definition. If A is the empty set, A is equal to phi. This is the Greek letter phi, okay? If A is the empty set, we define the probability of the empty set is always 0, or probability of phi, sometimes people write, is always 0. So that's condition number 3, or property number 3. Probability of the sample space is 0. Now, the next property is this. If event A is a collection of simple events, then probability of A is the sum of the probabilities of all the simple events. Now, this one may sound a little bit tricky. So let's say event A is rolling a die. Okay, if you roll a die, you could get 1, 3, 4. I just made it up. Now, 1 is a simple event, 3 is a simple event, 4 is a simple event. Why are these simple events? Because these events can happen only in one way. 1 is a simple event, 3 is a simple event, and 4 is a simple event. Again, why are they simple events? Because they can happen in only one way. So event A is a collection of simple events. So the probability of event A, which is the same as saying probability of getting 1, 3, or 4, is gonna be the same as probability of getting a 1 plus probability of getting a 3 plus probability of getting a 4. Okay, so that's exactly what this condition is saying, or this characteristic is saying. The probability of an event A will happen plus the probability that it will not happen is always 1. So again, let's leverage this example. If you roll a die, the outcome could be one of these 3, or the outcome could be none of these 3. Again, if you roll a die, the outcomes could be one of these 3 things, or not one of these 3. So that means you'll have either A or you will have not A. So not A, if A is an event, not A is the complement of A. It's called complement of A. Complement of event A, which is typically denoted by A prime. Some people use A prime, some people use A with a C on the top. I use A prime. Okay, so now what this condition is saying, probability of some event A plus the probability of its complement must always be 1. Probability of some event A plus probability of its complement must always be 1. And that's an important concept we will be using. So let me summarize what I said. Property number one, the probability must be between 0% and 100%, or it must be between 0 and 1. If you are talking about the sample space, which is the collection of all the simple events for an experiment, okay, then probability of the sample space is always 1. Easy way to remember, think of heads or tail, right? That's your sample space for rolling or tossing a coin, or sample space for rolling a die is 1, 2, 3, 4, 5, or 6, right? So if you toss a coin, you must have to have one of these outcomes. If you roll a die, you must have to have one of these outcomes. There is no other possibilities. So the probability of the sample space must be 1 or 100%. If A is an event which is empty event or empty set, then probability of the empty event or empty set is 0 by definition. If A is a collection of simple events, meaning events that can happen in only one way or unique way, then if A is a collection of simple events, let's call them A1, A2, okay, dot, 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 AN, there are n of them, then probability of A is gonna be probability of A1 plus probability of A2 plus dot, 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 plus probability of AN. Now I'm getting more mathematical looking, but conceptually it's the very same thing that I talked about. Like the example I gave you with 1, 3, and 4 for event A. So how probability of A was the probability of event 1, probability of event 3, probability of event 4. That's exactly what it is saying here, but in symbolic format. And the last characteristic, probability that an event will happen plus that it will not happen, is always 1. An event can happen or it cannot happen because things are binary, meaning one or the other. You can either jump and touch the rim for a basketball hoop, okay, or you can't. You either graduate from college or you don't. So it's binary outcome, okay, black and white, clear. So it is gonna be, if event A is an event, its complement is defined or denoted rather by A prime. We say probability of the event A plus the probability of event A prime is always 1. Okay, that's what it is. Now the next thing I'm going to talk about is this very important concept. Is called law of large numbers. This is something you may hear in conversation when people have discussion or conversations about things. People tend to use this term, law of large numbers. So what it is this: if an experiment is repeated large number of times, the proportion of times A approaches, proportion of time event A approaches the true probability is true probability of A, which is basically the frequency definition. Remember the example I gave you? It was this: if you toss a coin 100 times, 1,000 times, 10,000 times, 100,000 times, 1 million times, 10 million times, 100 million times, 1 billion times, 10 billion, 100 billion, 1,000 billion, trillion, whatever, right? If you keep repeating the process a large number of times, the percentage or proportion of times that event A happens divided by the total number is actually approaching the actual probability of the event. Like in case of tossing a coin, first time we had 0.55, second time we had 0.505 or something, third time we had 0.5005 or something like that. As you can see, all these numbers are approaching which number? 0.5. So law of large number tells you that if an event or if an experiment is repeated large number of times, then the proportion of event A approaches its true probability, which is P of A. That's what it is. A lot of definitions today, very useful definitions. And this is one of the more difficult sections of the semester you will be handling. And then there is one more topic, which is a little bit more difficult than this. I will cover it if time permits. Normally, it is not required by the course, and it is an advanced topic, but I normally cover it. But this semester, I don't know if I will be able to cover it. If I do, great. It's called Bayes' theorem. If I don't, I guess nothing I can do, right? Time is an issue. I have to cover the most basic stuff that we are required to. So law of large numbers we talked about. Now, let's go ahead and actually give you an example. 2x plus 1 is equal to 0. That's an equation. If I want you to solve for x, what do you do? Subtract 1 from both sides. On the left-hand side, you're going to get 2x because this is going to cancel, negative 1. Then divide both sides by 2. That's going to give you x is equal to 1/2. So that's the solution. So in the equation, 2x plus 1 is equal to 0. This x is actually unknown. You don't know what x is, but you can solve for it. If you solve for it, you know that it's a fixed number, which is what? Negative 1/2. If you plug in x equal to negative 1/2 here, negative 1/2, you'll see that the left-hand side will be 0, and so is the right-hand side. So it satisfies or it solves the equation, right? So in this equation, it doesn't matter whether I solve it, the 2x plus 1 is equal to 0, whether I solve it or somebody else solves it on another planet, or somebody else solves it from Bangladesh, I don't know, or some other countries in Europe, doesn't matter. The answer is always going to be x is equal to negative 1/2. So x is unknown, yet what? Fixed value. X is unknown in this equation, yet it is a fixed value. This is called deterministic. This is deterministic unknown. This is deterministic unknown. And it doesn't matter who solves it, that value is always negative 1/2. That's called a variable. This is called a variable. All of you have seen it in algebra. Now, in the context of probability, I am going to introduce a random variable, a variable as well. It's kind of like same variable symbol that we use. X is a variable. However, there is a world of difference between these two variables. In this one, the outcome is fixed, which is what? Negative 1/2. In this one, outcome is uncertain or random. Because if x is a variable, that's going to determine whether it's going to be a head or tail. If x is a variable, that's going to determine whether it's head or a tail. Let's say head is 0, tail is 1. So in essence, you are saying x is going to be either 0 or 1, right? But the difference between this variable and this variable is that this one is completely fixed, whereas this one is completely uncertain or random. You do not know. Only way you will know what value x will take is by actually tossing a fair coin. Okay, when you toss it, you either get a head or a tail. And that's why it's called a random variable. So I just introduced the concept of random variable. X is a random variable. It's a variable, but a random variable. Its value comes from a random process's outcome. Okay, its value comes from the outcome of a random process, or its value comes from an experiment or / trial. Remember, we defined these terms. Its outcome or its value, its value comes from the outcome of an experiment or trial, which we don't know. You can give a vaccine, so X could be the value, either 0 or what? 1. 0 means ineffective, 1 means effective vaccine. And you do not know what is the value of X gonna be until you test it, until you give the vaccine to the patient and observe the patient. That's when you know, oh, okay, the person has received the vaccine and it was effective, then X is 1. On the other hand, if the person received the vaccine, yet it didn't work, in that case, X is 0. Now, this value of X is completely random or uncertain, okay? Uncertain, and it depends on what the outcome of this experiment or trial gonna be. So this is the fundamental difference between a random variable and a variable. A variable, it is unknown but a fixed value, whereas a random variable, unknown but not a fixed value. Very, very important for you to know that. All right, the difference between a random variable and a variable. So if X is a random variable and it represents, so this random variable represents the outcome of a coin toss, outcome of a coin toss, right? Let's say 0 is head, 1 is tail. So X could be either 0 or 1, but you will not know the value of X until you toss the coin. Then you will find one of these two values and X is gonna pick that value. And it's gonna be different for different people. So if I do it, my random variable X is gonna give me one answer. It has to be one of these two, but if you try it, it might be a different answer, okay? If you try it, it might be a different answer. If somebody from Bangladesh tries it, it might be a different answer. If somebody from Germany tries it, it might be a different answer. Yet, we are dealing with the same experiment. So that's very important. Now, while I was teaching you guys this thing, random variable, something very, something fantastic came to my mind, but I don't know if you will find it that exciting. But it is very, very true. There is something called quantum mechanics. You may or you may not have heard of it. Quantum mechanics. In the quantum mechanical world, things behave very strangely. A particle, think of, for your sake, I'm gonna use a simple ball, okay? It could be, in the real world, you see it a ball, okay? But in quantum mechanics, it could be a wave, like a wave, or it could be a ball. You can think of, in a very simplistic way, you can think of it this way. Now, like this random variable, let's say when it's a ball, it's a 0. When it's a wave, it's a 1, let's say, coin toss. Now, in quantum mechanics, what happens, a particle can be either this or this. Okay, it can be either a ball or a wave. Now, you will not find it, what it is, until you actually check it, what it is. It's kind of like you will not know what the value of X is until you toss the coin and find out that it's a head. But in quantum mechanics, this is not so random as much. This is a bit of an advanced topic for you, but it's fun, something that could create curiosity. In the real world, an object is an object, right? It's hard and solid, and a ball is a ball. You can touch it, feel it, look at it, and whatnot. But in the world of microscopic world, in the microscopic world, or in the world of very small scale, it could be either this or this. Now, if you try to find out whether it's a solid ball, yes, you will find that it's a solid ball. But on the other hand, if you try to find out whether it's a wave, you will find that it is a wave. So it depends on what you are looking for. That's how it's behaving. It depends what you are looking for. That's so deceptive. That's crazy. You may think that, oh, that's weird, but it is fundamentally the universe is like this. Universe is the visible universe is amazing, but if you go into microscopic level, it's even more amazing. Like the concept of fixed things do not exist. It's all probabilistic. That's what we are talking about here. So if you observe a particle, you might find there is a certain probability that you will find it here. So if I ask you that, okay, where is this dot? You might be saying, okay, it's right here on the screen. But in microscopic world or in quantum mechanical world, you really can't say this ball is here. You might say that this is here, but by the time you say this is here, this is not here anymore. It's probably somewhere here. It's very, very curious world, very amazing world out there. Anyway, that's a little bit of diversion, but a good diversion. Hopefully you find it somewhat exciting, but I find it very exciting. All right, let's clear it off. So we talked about law of large numbers. We talked about random variable. About random variable, one thing you must remember, it's a variable, but the outcome is uncertain, unlike the regular variable. For the regular variable, everybody is going to get the same solution, same value. But for random variable, you don't know who is going to get what, okay? One person might get this, the other person might get that. It depends on the experiment or each trial. Now I'm going to do some stuff here. A is a set, so this is kind of set theory for you a little bit. A is an event or A is a set. B is a set. So A union B means you are uniting the sets of A and B. So let's say A is 1, 2, 5, and B is 1, 3, 5. Then A union B is going to be union of these two sets is going to be 1, 2, 3. Oops, what happened? 1, 2, 3, 3, and 5. 3 and 5. Even though 5 appears in both of them, both of these sets, you do not write it twice. It's just the presence itself that counts, okay? It's just the presence itself that counts. So that's A union B. Now A intersection B means this, or sometimes we say A and B, means whatever is in A is also in B. That means what is common in both of them. As it turns out, it's 5 that's common in both of them. So A intersection B is gonna be 5. Whereas A union B is gonna be whatever is in A plus whatever is in B, making sure that if a term or an item is repeated, you don't write it multiple times. You just write it once. It's just the presence, okay? 5 is appearing twice, but we don't write twice 5. We write just once. So that's A union B and A intersection B. Now let's consider rolling a die. Roll a die. Okay. So what it is going to be, let's say event A is 1, 3, and 5. That's event A. Remember, we are talking about rolling a die. then my complement of A is going to be what is not in A. Remember, A complement means what is not in A. So what is not in A in the context of rolling a die? If you roll a die, you get 1 through 6, right? So 1 is here, 2 is not here, so 2 must be here. 3 is here, 3 cannot be in A complement. 4 is not in A, 4 must be in A complement. 5 is in A, so 5 cannot be in A complement. 6 is not in A, so 6 must be in A complement. Do you see? A and A complement or A prime, they don't have anything in common, okay? And A complement is whatever is not in A in the context. So let's say if my event A is getting ahead, if I am rolling a die, tossing a coin, then my A complement in the context of tossing a coin is going to be just tail, T. Do you see? If I denote this by 0, this by 1, so then it's going to be A is going to be 0, A prime is going to be 1. So it depends. So if A is the event, you pass this class, okay? So A complement is the event, what? You do not pass this class. Okay? So A and A complement. Remember, I told you probability of event A plus the probability of its complement is always 1 or 100%. So this set theoretic notation, please try to remember, A union B means the union of both sets. A intersection B, which is this, means what is common or what is present in both of these sets. Concepts of set is fundamental to mathematics. Two events are disjoint if A intersection B is the empty set. Okay, that means nothing common. Two events are disjoint if A intersection B is empty set. Another way of saying the same thing in ordinary person's term or in layman's term is this. Two events are disjoint if they can't happen at the same time, right? They can't have something common. Like if A is 1, 2, 3, if you're rolling a die, B is 2, 5, and 6, these two events are not disjoint. Why not disjoint? Because they can happen at the same time. Why? Because if you roll a die, you get 2, then A has happened, then also B has happened because B has 2 too, right? If you roll a die, you get 2, then A and B both could happen. So A intersection B in this case is just 2. So these two events are not disjoint, not disjoint. Whereas event A, 1, 3, 5, event B, rolling a die, again, we're talking about 2, 4, these are disjoint. Why? Because A intersection B is empty set. There is nothing common between the two. So two events are disjoint if their intersection is empty. Now, let's talk about the next rule. It's called the addition rule for probability. If two events are disjoint, meaning there is nothing common between them, then probability of A union B is equal to probability of A plus probability of B. Remember, A intersection B is empty. That means disjoint. A intersection B is empty, meaning disjoint. On the other hand, if they are not disjoint, in that case, the formula is going to be this. Probability of A union B is equal to probability of A plus probability of B minus the probability of A intersection B. Now, it's easy to use a diagram. It's called Venn diagram. So I'm going to use this. So think of this event A, event B, right? If you think of probability of A union B, then think of this overlapping position, overlapping region. When you're calculating, so let's say this circle represents the probability of A, this circle represents the probability of B. You can think of this middle portion is being counted twice, is being counted once with A and another time with B. So if you count it twice, whereas you should be counting it once, you just subtract it once. That's what you see here. You are subtracting it once. You are subtracting it once. So that's what it is. Since you have the Monday off, I'm going to take a little extra time today and I'm going to work on this problem. Then I will let you go. This will give you enough information to solve the homework problems. So let me just go ahead and take a little extra time for today. And I'll probably go up to 11. So please bear with me. We are going to use this formula. First, your chances of passing statistics is 80%, and your chances of passing organic chemistry is 70%. The probability that you'd pass both of the classes is 55%. Answer the following questions based on the above information. Let me draw a diagram that will help you. So your chance, maybe not. I'm gonna create this, create that. This is not proportionate. So we are in the universal set U, okay? Universal set U. That's what it is. What it means is that everything that relates to taking two class is contained within this square, within this rectangle. And inside you have the prob events. So event, so I'll call it event S and event C. S is for statistics, C is for chemistry. So big circle represents the probability, event that you pass statistics, and the other circle, C circle, represents that you pass chemistry. And there is an overlap between the two, which is 55%, they tell you, okay? So if S represents the probability that this left circle represents the probability that you pass statistics, which is 80%, so this should be 0.8. And on the other hand, chemistry 0.7, because there is a 70% chance that you will pass chemistry. And then there is a 55% chance that you will pass both. So this middle portion is going to be 0.55. It's not proportionate, remember. The left circle represents 80% of the area, right circle represents 70% of the area, middle overlapping portion represents 55% of the area for both of these circles. Now, is there a problem because the probabilities do not add up to 100%? If you look at the probabilities, 80% plus 70% plus 50% is well over 100%. But remember, the probabilities have to add up to 100%. It cannot be more than 100%. As a matter of fact, probability of the sample space S is always 100%. It has to add up to 100%. Now here we see that it's not adding up to 100%. Is there a problem? The answer is no. Why? Because of this overlap. Because look, overlap is 0.55 or 55%. You counted it twice, once with this one, once with this one. So if you subtract once, it's going to come down below 100%. Okay, so 80% plus 70% minus 55%, which is, by the way, 95%, you can see. So it's coming down below 95%, below 100%, but it should actually be exactly equal to 100%. We'll talk about it shortly. So it's not a problem. create a Venn diagram. I did it. Find the probability that you just pass statistics. So this is where you kind of need to think. Find the probability that you just pass statistics. Okay, you just pass statistics. Now, this circle represents the probability that you pass statistics. But remember, this middle guy is, or 55% chance that if you pass statistics, you'll also pass what? Chemistry. But we don't want the chemistry part. We want the statistics part. So how do I find this region? It's 80% minus 0.55. So 0.8080 minus 0.55 is 0.25. Or there is a 25% chance that you will pass only statistics, just statistics. What is the probability that you pass only one of the two classes? That means you either pass statistics or you pass the other one, chemistry. Again, the similar argument will show for this circle, 70% minus 55%, 0.70 minus 0.55, which is equal to 0.15 or 15%. Okay, so the probability that you pass only one of the two classes is you either pass statistics, which is 25%, plus you just pass chemistry, which is 15%. That's going to give you 40%. Okay, that is going to give you 40%. Find the probability that you pass at least one of the two classes. So that's kind of tricky. At least one of the two classes. So that means at least once, probability of at least one. At least one means probability that you pass one class. Or now I'm going to start using the variable. Probability that x is equal to, x is the random variable, x is 1, plus the probability that x is equal to 2. That means you either pass statistics, statistics or calculus, not calculus, chemistry, plus the probability that you pass both statistics and chemistry. So now we found the probability of x equal to 1. That means you exactly pass one of the two classes, not both, which is 40% right here. So it's going to be 0.4 plus probability that you pass both of the classes, meaning x is equal to 2, which is 0.55. So 0.55. So 0.44 is 0.40 plus 0.55 is 0.95. Now the last thing is this. Find the probability that you pass neither of the classes. That means you fail both. Probability of failing both classes. Okay. Now look, if you are inside of these two circles, you will be passing at least one of the two classes. If you are inside of these two circles, you will be passing at least one of the two classes. But if you're outside of these two circles, that means you're going to fail both of the classes. Okay, and what is that? Now, you need a little bit of thinking here. Remember, the universal set U is 100% or 1. That means you have to be within this rectangle, minus all the circular regions, which is 0.25, the left one, 0.25, minus 0.55, the middle section, overlapping section, minus the right side, which is 0.15. If you add these numbers, you're going to get 1 minus 0.95, or 1 minus 0.95 is 0.05, which is 5%. There is a 5% chance that you will fail both of these classes. There is a 5% chance that you will fail both of these classes. That's what it is. So that's a very complete example. Now I'm gonna do the, maybe next time I'll do it, this time not. I'll show you how to do the problem in a different way, okay? Exact same problem, but in a different way, you'll get the exact same answers, but this is the best and easiest way of understanding. Create a Venn diagram and do it step by step. Particularly pay attention to this overlapping region, okay? Because this is being counted twice. That's why you need to subtract it once, okay? Now let's go ahead and do another problem before I let you go for the day. So now you should be able to do the next problem. Ignore this problem for now, okay? This problem, ignore it because I'm gonna cover it later. This is conditional probability. Now this is the one I kind of want to go over. If you roll a die once, we define the following. So roll a die once and we define the following events. A is 2, 4, 5, 6, and B is 1, 3, 4, 5. Okay, these are the two events. Answer the following questions based on the information, on this information. Is event A a simple event or a compound event? Okay, so I guess compound event, that's the term they use. So I said complex event. It's a compound event in the earlier part of the video. So is it a simple event? Anybody? For A, is event A a simple event? A is 2, 4, 5, 6. You're rolling a die. Is it a simple event or not a simple event? Anybody wants to?
It wouldn't, right? Because remember, the outcome of 5 can happen in A and B.
Your answer is correct, but reasoning is not correct. I'm just talking about event A only, not for now, ignore B.
Okay.
It is not a simple event. Why? A can happen in 4 different ways. If you roll a die, you get a 2, A has happened. If you roll a die, you get a 4, A has happened. If you roll a die, you have a 5, A has happened. If you roll a die, you get a 6, A has happened. So in essence, A can happen in how many ways? How many
4.
ways? 4 different ways. So remember the definition of a simple event? It can happen in only one way, but A can happen in 4 different ways. So it's not a simple event. In exactly the same way, using the same reasoning, B can happen in 4 different ways. So it's not a simple event. So neither A nor B is simple event. Are A and B disjoint? That means you are trying to find not probability, sorry. Is A intersection B empty? Empty set, question mark. What is A intersection B? That means what is common in both A and B? Is there anything common that is both in
5.
A and B?
The 5?
5 is common. Is there anything else?
No.
4 is
4 as well, sorry.
4 and 5 both are common. So this is not the empty set. So are these disjoint? No. Let's find the probability of A. If you roll a die, what is the probability that you will get A? How many ways can A happen? 4 different ways. That means if you get a 2, 4, 5, or 6, you will get an A, right? Event A will happen. If you roll a die, if 2, 4, 5, or 6 shows up, then event A has happened. So that it has to be divided by the number of simple events, which is 6. So that's going to be 2 goes into 4 twice, 2 goes into 6 3 times. So it's 2/3. What is the probability of event B? Exactly the same way, 4 out of 6, which is 2/3. What is the probability of A union B? A union B. A union B is 1, 2, 3, 4, 5, and what? 6. A union B is 1 through 6. So what is the probability of A union B? Can anybody quickly tell me? This should be an easy one. You're rolling a die. If you roll a die, can you get anything other than these numbers?
No.
So this must be your sample space, right? S. So the probability of the A union B is nothing but 1, which is what? 100%. Probability of A intersection B. A intersection B is 4 and 5, right? We found it over there. A intersection B is 4 and 5. So how many ways A intersection B can happen? 2 different ways, because if you roll a die, you get a 4 or you get a 5, is gonna be A intersection B. So which is 2 out of how many? 6, which is 1/3. 2 goes into 6 3 times. I think there are a couple more, so let me just clean it up. A complement, what was A? Great, I lost it. 2 4 5 6. A is 2 4 5 and 6. What is A complement in this case? Is gonna be what is not in A but could potentially happen. 1 3, and that's it. A complement is this. So what is the probability of A complement? A complement has 2 items, which are simple events, 2 out of 6, which is 1/3. 2 goes into 6 3 times. B, what was B? Let me go back to B. 1 3 4 5. B is 1 3 4 and 5. And B complement is what is not in B, which is what? 2 and 6. 2 and 6. So what is the probability of B complement? Is 2 out of 6. And the next one I think I ask is A complement union B complement. A complement union B complement. So A complement is this, B complement is this. So if you union them or put them together, you're gonna get 1 2 3 and 6. So the probability of A complement, probability of A complement union B complement is gonna be 4 out of 6, which is 2/3. 2 goes into this twice, 2 goes into this 3 times. Okay, anything else? I think that's all. All right. That's all I wanted to talk to you about. And for the next class, please go ahead and read the next few pages. Bayes' theorem, don't read it. If time permits, I'll do it towards the end of the semester. But if we don't get time, then I'll go ahead and skip it. But this is an amazing topic. It has a lot of practical implications, practical usage, real world. I am really, really excited to be able to teach it, but hopefully we'll be able to make some time, okay? All right, so go ahead and read these few pages up until here, and I'm gonna put an assignment online, and I haven't covered these topics, so there will be problems from this topic, conditional probability, but just ignore those for now. And when I cover it in the next class, which is Wednesday, a week from today, we will be going over this, and you will be able to do the homework, rest of it. But many of the homeworks you should be able to do right now. All right, folks, you guys have a wonderful weekend, long weekend, President's Day weekend. Be very careful. This is a very serious time. I want you to be very careful and stay safe and healthy. Don't mingle with people. Do social distancing, wear masks, okay? Wash your hands, or use gloves, whatever it is. Make sure that you stay safe, okay? Don't socialize unless, basically don't socialize. There is no unless. You don't want to get sick, okay? Stay safe and stay healthy. Take care.
You too.
Thank you. You as well.
Thank you. Thank you.